In this lecture, we'll talk about the Laplace transform of step functions. So before we can, think about Laplace transform of step functions, maybe because we want to think of a functions, any of the functions f, in terms of a step functions by assigning a step for it, right? So we can consider the related function g of t that related to the function f of t by these definitions, right? And you have g of t is a step function of f of t, or is cousin functions of f of t in terms of step functions. When g of t equal to 0 for t less than c, and g of t equal to f of t minus c, where t is at least c. So f of t minus c just means you take the function f of t and you shift it to the right c unit. So this is f of t, f of t minus c is this function, and the red function is f of t. Okay. So the reason why we want to consider this function is because, again, we want to think of a functions in terms of the step functions. If we have a step function in this form, then we can use the Laplace transform onto the step functions to find the solutions to a initial value problem. All right. So now the function g of t here will be rewritten in the terms of u c t and f t minus c. Okay. So as you see before that, the unit step function or the Heaviside function will have just u c of t. That means the function is just going to be 1 instead of the functions. Now you have a real function instead of just 1 as the unit, as the value. Okay. So the function g of t is going to be in this form right here. An illustration for this g of t is very similar to this graph. When you have the function f of t, let's say f of t here, right? And I have c here. Then I will move, and then the functions f of t will be f of t minus c will be here. This is f of t minus c, okay? And the unit function g of t is this functions right here. So it's everything equal to 0 up to the point t equal to c, and then everything will be f of t minus c after the point c. So this is, we'll say, erase this. This is the function g of t. This is how it looks like. The green functions here is a function g of t. Okay. Now, so that's just the introductions on how to think of functions in terms of a unit function, and how you can define a related function g of t as a unit functions in terms of the function f of t. Okay. Then the next thing is you can use the definition of Laplace transform at its inverse. You can come up with the following formulas. First, if you find the Laplace transform of just the unit functions u of c, in this case here is the unit functions here, 0, c, and then 1 after c, right? It's gonna be e to the negative cs divided by s, for s is positive. So the Laplace transform of just the unit functions equals to this functions. C here is a step. And vice versa, the inverse of e to the negative cs equals to the unit functions uc of t. Okay. All right. So using the definitions, we find this formula. And then in general, if you have, because remember we was like shift t, f of t here. This looks familiar because this is the function g of t that we found here. Okay, and then if you want to find the Laplace transform of this functions here, it's gonna be equals to e to the negative cs multiplied by the Laplace transform of f of t. And is equals to e to the negative cs multiplied by big F of s, which is because big F of s is the Laplace transform of f of t. Or if you have a function, a unit functions, you see f of t, then the Laplace transform of this function will be equals to, again, e to the negative cs multiplied by g of s, where g of s is the Laplace transform of f when of t plus c. Okay, either forms are the correct form for you to find the Laplace transform of unit functions. Okay. And conversely, if you find in the inverse of a Laplace transform of the unit functions in this form, if you see a Laplace transform in this form, you know that this is unit step function. And if it's a step functions, then you can use C to determine the step. You can use big F of S to determine the functions, f of t minus c. Okay. Well, let's look at a few examples. Let's try to do some examples just to make sure that we understand how to find the Laplace transform of a unit step functions here. How to find the inverse of the Laplace transform relating step functions here. Okay, remember you always have f of t, and then you have to convert it back to f of t minus c, or you have to start with the f of t minus c in order to come up with the correct form. Or if you start with the f of t, you see f of t, then you have to find g of s, where g of s is the Laplace transform of these functions right here. Okay, it sounds a little confusing, but it will be more clear once we do a few examples. Now let's look at the next example here. We're given a piecewise functions, step pi, 2 pi, right? Before we can try to find the Laplace transform of these functions, maybe it's worth it to convert it into a unit function. So f of t, we have 0. So we start with 0. So it's just 0 plus, but I just put it here. And you have pi of t, you have pi of 2t. 2 pi, u of pi of t, 2 pi. So there's two steps right here. In order to find the coefficients, I have to take this value and minus the previous one, which is t minus pi, right? That's minus 0 plus. And in order to find the coefficients or the functions here, I need to take this and minus the previous value, which is 0 minus t minus pi is going to give you pi minus t. Just change the order. So if I combine everything together, my functions f of t in terms of unit function should be equals to u pi t minus pi plus u 2 pi minus t. All right. And now my goal is I want to find the Laplace transform of f of t. But look at this formula here. In order to find the Laplace transform in a nice way, I have u of c, right? And I need to have f of t minus c. Okay. So the functions I'm looking at right here is the function t. T is the functions, and t here is also the functions, f of t. But because I have c pi, and then pi is the unit. That means my function t has to be in the form of f of t minus pi. And luckily, this is in the correct form, t minus 5. Okay, so then I can just leave it alone. I don't have to do anything with the first function. I can convert it to the Laplace transform by taking e to the negative cs. So c is pi, so negative pi s. And multiply by the Laplace transform of t, of the function f of t. And the function f of t in this case is t. Okay, Laplace transform of t is 1 over s squared. All right, so this is the Laplace transform of the first unit function. How about the second unit functions? I have 2 pi. And again, the functions here is still f of t, or you can move it f of negative t, right? So the f of t, f of t equals to, again, I can either assign t or negative t. So let's assign s of negative t, okay? Because I want to take this variable. And before I can use the Laplace transform of f of t, I need to convert this into f of t minus c, where c is 2 pi. So, and this, you can take this functions here, and then you do it on the side a little bit, just this one. So I want to have, because my function f of t is negative t, that means f of t minus 2 pi is going to be negative t minus 2 pi. It's going to be negative t plus 2 pi. Okay. So I need to have negative t plus 2 pi so that I can put in this form. I can put in this form so I can use this f of t equals negative t as my function f of t. But then in the original form, I have pi minus t. How can I find 2 pi minus t? So this function's right here, right? I can rewrite it in terms of u2 pi. I need 2 pi, so I need to add 1 pi. So if I add 1 pi, then I have to subtract 1 pi. So I have 2 pi minus t minus pi. As you can see that I didn't do anything fancy. I add 1 pi here to get this form. And then I have to subtract another pi to resolve the equivalency. Okay, so I transform this to 2 pi minus t minus pi because I can extract this out. So it's going to be u2 pi of 2 pi minus t minus u2 pi times pi. Okay. So from u2 pi minus t here, this is the form that I want, right? I can go back here, and I can find the big F of t. If ft is negative t, so then big F of s is going to be negative 1 over s squared. Okay. Then the result for this will be, so the Laplace transform of this functions here is e to the negative 2 pi, right, which is c here, s, multiplied by negative 1 over s squared. And then the Laplace transform of this unit's functions here, because pi is a constant, so then it's just going to be pi e to the negative 2 pi s over s. Because the Laplace transform of units step function uc, it's just going to be e to the negative cs divided by s. And I multiply by pi because you have pi here as a coefficient, right? So I found these 3 pieces here. This piece, this piece. And remember the negative sign, and I'm just gonna combine all this together. So I'm gonna, so for this the Laplace transform of this unit functions is these two unit functions added together. Let's see, I can move it down a little bit so we have more room here. So first, this will go to e to the negative pi s, and this is divided by s squared, right? And then this one, we found that it's going to be negative e to the negative 2 pi s divided by s squared and minus pi e to the negative 2 pi s divided by s. Okay, and then you can combine these three together. I have s squared is in the denominator, right? I can take e to the pi s on its own, negative e to the, I have s squared here, e to the 2 pi s, negative 2 pi s. And then I can combine these two terms together. 1 plus, you have s here, you have s here, s pi, which is going to be your Laplace transform of this unit functions. Again, you have to convert this functions into the correct form. So first you have to identify the function that you're going to use, right? So then you can find the f of s. And then you have to make sure that it's in the correct form, t minus 2 pi, because 2 pi is a unit, is a stepped. And then in order to, then you have to use algebra to manipulate this into the correct form. And then just take care of the rest. And you split this into two different unit functions. And one of them is in the correct form, another one you can use a form of a constant multiplied by a unit step functions. You find out these two transforms, combine these two with the first one here. And luckily the first one is already in the correct form, so we don't have to do anything with it. We just need to convert it from here. And just a reminder that big F of s here is going to be 1 over s squared. So that's why I multiplied this by 1 over s squared to get this transform. All right, so this is how you find the Laplace transform of a piecewise functions, right? Or of a unit step, or of a step function. Now, if you have the Laplace transforms and you want to find the original function, or you want to find the step functions given this Laplace transform, how can you do that? Well, first, this is just a Laplace transform, and you recognize it's going to be a step function because of this exponential. So this is stepped functions, right? Where the step c equals to 3. And besides this, you recognize that 1 over s minus 2 squared plus 16 in Laplace transform is the form of sine 16 is 4 squared, sine of 4t, okay? But in order to, for sine of 4t, this is gonna be just s squared plus 416. But then in here you have s minus 2, then you have to think of, oh, because you shift it to the right by 2, so you should have another exponential functions e to the 2t. Okay, because you have the 2 here. Is the 2t sine 4t, but the sine 4t here, remember, if you want to have sine 4t as a functions So the Laplace transform has to be 4 over sine squared plus 16. Now you're missing the 4 here, so you have to multiply by 4 and you divide it by 4. That tells you that this is going to be 1 over 4. Right? Okay. So you recognize the form of it to find the original functions, right? So you say Laplace, the inverse of this function should be step functions in terms of sine and e to the 2t. So the step is c, so you will have u3 of t, right? And then you know that you recognize this. This is like u e to the negative cs multiplied by f of s. And by the definition here, you should have here, you should convert it back to u ct and f of t minus c. So it equals to u ct f of t minus c. So I just want to rewrite the formula just to remind us. And we know that f of s here is a form of these functions right here. Okay. Well, let's put everything together. We have u3t f. What is function? This is a function f of t. And if this is function f of t, then f of t minus c should be 1 over 4 e to the 2 t minus 3 sine of 4 and t minus 3. So this is the Laplace transform. This is the inverse of the Laplace transform in terms of unit function. And this is how we figure it out. We recognize the pattern and try to find big F of S. Once you found the big F of S, then you can find F of T in the correct form. And then you can use this formula here to find these functions right here in terms of this. Okay. As you can see that the Laplace of this is going to be the units function that you found here. Let's see, here you have 4. You're missing 4, so you have to multiply by 4 to get to the sine, and it's going to be 1/4 of sine. And it's 1/4 of sine, so it's just, again, 1/4 here, it's just a constant. You can move it out, and you can put it here. It's constant. When you change it from t to t minus 3, it does not affect 1/4. You just keep it there. All right, so this is the unit functions that you can find for this inverse Laplace transform. Let's do another one. And this one, again, you find the inverse. And you recognize this is the units function because e to the negative s, so that means c equals to 1. So you have u1t, right? And then you have to figure out the functions here in terms of this. So you know that this is the form e to the negative cs, big F of s, right? And then if you can find t, then it's going to be uct f of t minus c. Okay, so that's the goal here. Well, the next things we want to do is we want to find the big F of s here using this. So this is the a sum of 2 different functions. Well, at first, I consider these functions first. We have factors in the denominator, then we think of using partial fractions. So partial fraction, we split it in 3 different forms, right? 3 different fractions because you have 3 factors here. S squared, cs plus d over s squared plus 4. Okay, and then from here you will try to combine them together. So I will combine them right now. So you have a s squared plus 4 plus b s squared plus 4 plus cs plus d times s squared. Okay, so this is gonna be equals to as cubed plus 4as plus bs squared plus 4b plus cs cubed plus ds squared. And you know that this is gonna be equals to 1. Okay, so there's only one constant on the right side. That means you can cancel some of the term here. So q a plus c equals to 0. Square b plus d equals to 0. A, 4a equals to 0. And 4b equals to 1. So that means b equals to 1 over 4th, a equals to 0, and c should be equal to 0, and d should be equals to negative 1 over 4. Okay, so we have b, we have d, are the only non-2-0 terms, so we can rewrite this in terms of a is gone, b 1/4 over s squared, d, c is gone, so plus negative, because it's negative 1 over 4 s squared plus 4, right? And your goal is you need to find the Laplace of this. So what is the Laplace of, this is the Laplace transform, and you need to find the inverse. One over s squared is t, so 1 over 4t. This is s squared plus 4, reminds us of, and you have a constant here, so it's going to be sine, right? Sine of 2t. This is because this is 2 squared, and you need to have 2 here, and you need to divide it by 2 here. So this is going to be, you extract this to get sine 2t, and left over is 1 over 4 divided by 2 is 1 over 8. So this is the Laplace transform of this first fraction. Okay. How about the second fraction? Again, we just have to do partial fractions. 4, and this is going to be a over s plus bs plus c over s squared plus 4. And again, just combine them together, right? A s squared plus 4 plus bs plus c multiplied by s. Divided by s and s squared plus 4. Okay, well, then you can just keep distribute it out. So you have a s squared plus 4a plus bs squared plus cs. Okay, I'm just going to use the top right now, and it's equals to 1. So what does it mean? That means this term will be equals to 0. A plus b equals to 0. cs equals to 0. So c equals to 0, and 4a equals to 1 means a equals to 1 over 4. C equals to 0, and then b equals to negative 1 over 4. All right, now go back to our, so we know that a is 1 over 4 s plus b c0. So this have negative 1 over 4 s divided by s squared plus 4. So this is, and again, we want to find the Laplace transforms, the inverse of this. One over s, the inverse of 1 over s is the constant, right? And multiplied by 1 over 4th, it's just going to be just 1 over 4th. And this is cosine of 2. All right, so look, I found the Laplace transform of these two pieces, and I know that it's a unit function, so I just have to convert it to f of t minus c. And again, c is, in this case, is 1. So the answer is the Laplace, the inverse of e to the negative s of 1 over s squared plus 4 plus 1 over s squared plus 4 equals to uc, as we already know, and c is 1, so it's just u1t, and multiply by the first is this functions, but in terms of t minus 1, so it's going to be 1 over 4th t minus 1 minus 1 over 8 sine of 2 t minus 1. Okay, again, this is what I get from here, but I converted to t minus 1. And then my second piece is here. You have, let's change color so you can see it clearly. 1 over 4th is just 1 over 4th. It doesn't affect it. And you have a plus in front of it, so it's 1 over 4th. And then minus 1 over 4th cosine of 2 t minus 1. So this should be the answer for the inverse of Laplace transforms in terms of step function. As you can see that later on when you have an initial value problem, right, where step functions involved, then you have to find the Laplace transform of the step functions, and then you have to solve for the Laplace transform. And then after that, you have to convert it back to the original function to find the solution to an IVP problem. But then again, this lectures here helps you to figure how to convert a step function into its Laplace transform. That's the first step. And then once you solve for the Laplace transform of the solutions, then you know how to convert it back to the step functions to find the solutions, right? All right, again, it looks complicated, it looks confusing, but if you practice enough, pretty sure you will get a grasp of it.